Charlie.
Hey Wade, now let's actually dive into some examples with a few special cases where it makes more sense to look at the complement. So it says to start off, we're going to list these two special cases below where it's easier to look at the probability of the complement of the event rather than calculate the probability directly. So there's two cases that I definitely think this is easier for. And the first one is if we're looking at the probability of at least one of something. So I'm going to list the rules and then kind of explain why we use them with our puzzles. So I'm going to just write this down that the probability of at least one something, the complement is going to be, we're going to do 1 minus. And then if I think about kind of the opposite chance of at least one, it's actually the probability of none. So none and at least one are complements, and more on that in a minute. The second special case is actually the probability of not all of something. So this one's a little kind of more straightforward to remember. The complement of not all is just all. So we have 1 minus the probability of all. So let's actually do our examples to see why this is the case. So the very first question says, what's the chance of drawing 5 cards? So we're looking at 5 different probabilities multiplied together from a deck with replacement and getting no hearts. So that means we're going to get a non-heart and a non-heart and a non-heart and a non-heart and a non-heart. And now that we know these two special cases, I want to ask myself, do I need to use them? So the chance of getting no hearts, is that the same thing as getting at least one heart?
Probably getting no heart? No.
No, right? Yeah, at least one heart would be getting, at least for drawing 5 cards, that would be technically getting 1 heart or 2 hearts or 3 hearts or 4 hearts or 5 hearts. No hearts is just one thing, right? It's just getting 0 hearts.
Yeah.
This is the real question though. Is no hearts and not all hearts? Is that the same thing?
No hearts is 0 hearts. Not all hearts could be anything but 5, right?
Anything but 5, right? That's exactly right, Wade. They sound kind of similar, not all hearts and no hearts, but they're actually very different. I always like to remind students, think about your grades. If you're taking 5 classes, let's say we're taking 5 classes this semester, and you told your parents that you got no A's at the end of the semester.
Ooh.
That means you didn't get an A in any of your classes. But if you said something like not all A's, that's a little more ambiguous. No A's means 0 A's. But what would actually be considered not all A's if we're taking 5 classes?
I mean, I could have just gotten 1 A.
Yeah, you could have gotten 1 A. You could have gotten 2 A's. You could have gotten 3 A's.
4 A's?
4 A's.
I just know I didn't get all 5 A's.
Yeah. Could you get 0 A's? That'd be not all A's, right?
Yeah.
So I could even add that. So it's everything except all 5 A's. So these are not equal, basically. And that's a really common mistake that students make is they see no hearts and they think, oh, do I have to use the special case? Well, no, because I only want to use these two if it says the words not all or at least one. So I can just calculate this directly. I can say, what's the probability of getting no hearts? So again, I would multiply 5 different probabilities together. And for the first one, what's the probability of not getting a heart?
So when I initially have the deck, 3/4 of a deck is not a heart.
Right, exactly. So I can say the probability of not getting a heart is 3/4. Also, if we think about 52 cards, that would technically be 39 out of 52 cards because there are 13 hearts. And then we're drawing with replacement. So I'm going to take out that non-heart and put it back in. So what's the probability of not getting a heart on the second draw?
Since you put it back in, it's the same deck, so they're independent. So it's going to be another 39 out of 52 or 3/4.
Exactly. So I'm just going to add that for all the remaining probabilities. So Wade, in Python, you can do 3/4 star 5.
So 3/4 to the 5th power. And that is 23.7%.
23.7%.
Or as Python shows me, just 0.237.
Exactly. So this was just a classic case of the multiplication rule. I didn't need to use my special cases because it I could just calculate it directly. So puzzle 2 says, what's the chance of drawing 5 cards from a deck without replacement and getting at least 1 heart? So with this one, I see right away that it says getting at least 1 heart. And I know that if I look at special case number 1, it says the words at least 1. So it's going to be easier for me to find the probability of getting at least 1 heart using the complement. So I'm actually going to find 1 minus the probability of getting no hearts. And that's going to make my life a lot easier. So you might be wondering, why is that the case? And I always like to think about kind of the sample space in this case. I can either get, if I'm counting hearts and drawing 5 cards, I can either get 0 hearts, right? I can get 1 heart, I can get 2 hearts, I can get 3 hearts, I can get 4 hearts, or I can get all 5 hearts. Those are all of my options. That gives me 100% of my options. And at least 1, if I want to know which of these options fall into the category of at least 1, it would actually be everything except the 0 hearts, right? 1 heart would be at least 1 heart, so would 2 hearts, so would all 5 hearts. So at least 1 is all these different options. These are all at least 1 heart. So if I calculated that directly, I would have to figure out the probability of getting 1 heart or 2 hearts or 3 hearts or 4 hearts or 5 hearts. That's too much. I don't want to do that. But I can look at the opposite chance, which the only thing that doesn't fall under the category of at least 1 heart would be getting 0 hearts or no hearts. So I can just find that probability, subtract it from 100% or 1, and that will give me the probability of getting at least 1 heart. So that's why this rule makes our life so much easier. All I have to do is say, for my answer, 1 minus the probability of getting no hearts. And we know on our first draw, what's the chance of not getting a heart?
The probability of not getting a heart is going to be all the other cards, or 39 out of 52.
Exactly. We have 39 out of 52. And this is a little more complicated because it's without replacement. So I want to get a non-heart and a non-heart. So for the second, the probability of getting a non-heart, given that I did get a non-heart on the first one, would be 38 out of 51. And I'm drawing 5 times. So for the third card, I want to get a not heart. And I've already taken 2 of them out. So this would be 37 out of 50. For the fourth card, it's going to be 36 out of 49. And then 35 out of 48. So essentially what I'm doing here is I'm looking at the right side of this equal sign. I'm just focusing on 1 minus the probability of getting no hearts because that's easy to calculate. And I'm kind of ignoring this at least 1 heart because that's complicated and they're equivalent. So if I find one, I found the probability of the other. And Wade, when you put that into Python, what did you actually get?
So I haven't done the 1 minus yet. So
Okay.
just the ending part. I got 0.2215.
0.2215. So I have 1 minus 0.2215 as my answer. And that ends up giving me
0.7785.
0.7785 or 77.85%. And that is my answer. It's a pretty high probability, but if I have a 1/4 chance of getting a heart, then the probability of getting at least 1 in 5, if I'm drawing 5 times, that kind of makes sense. So that's a case where calculating this directly would have taken way longer than using that special case. Let's go ahead and do a few more. So the next one says, what's the chance of drawing 5 cards from a deck with replacement and getting all diamonds? So what's the probability of getting all diamonds? And Wade, do you think I need to use one of my special cases here? Am I asking for the probability of at least 1 diamond?
Nope.
And not all diamonds?
Nope.
Nope, just the probability of getting all diamonds. So here, and this is with replacement, which is nice. Our deck doesn't change. So our first probability is going to be the same as the second and the third and the fourth and the fifth. So here, the probability of getting a diamond is going to be what?
So we've got the full deck, so it's 13 out of 52.
And I'm just going to save some space, I'm just going to raise that to the 5th power because I'm going to put that diamond back in. And then when I draw again, the chance of getting a diamond is also 13 out of 52. So what does Python give us, Wade?
So 13 out of over 52 raised to the 5th power is 0.00095. 976.
0.000
Zero. Three zeros.
976. Or I guess I could write this as 0.0976%. Thank you. So the probability of getting all diamonds is pretty low.
Very, very low.
Next, it says, what's the chance of drawing 5 cards from a deck without replacement and not getting all diamonds? So
Ooh, that word's remaining sounding familiar.
that word sounds familiar. Not all is our special case. So here again, I'm going to use my rule. The probability of not getting all diamonds is actually going to be 1 minus the probability of getting all diamonds. And the reason we're going to do this, again, if we think about drawing 5 cards, I could think about this idea of the sample space. I can either get 0 diamonds. Diamonds are kind of hard to draw. I can get 1 diamond. I can get 2 diamonds. I can get 3 diamonds. I can get 4 or 5 diamonds. And if I think about what not all diamond means, not all diamonds mean 0 diamonds would be not all diamonds. So would 1, so would 2, so would 3, so would 4. The only thing that wouldn't be included in this not all diamonds, so this is not all diamonds, that's all those probabilities. I don't want to find them. Instead, I can just do 1 minus the probability of getting all diamonds because all of these added together is 100%. So that's where this rule comes from. So instead of focusing on the complicated not all, I'm just going to find 1 minus, and now I'm just going to focus on the probability of all. So that means my first draw, I get a diamond. So wait, what's that probability?
So they're full deck. So we got 13 diamonds in that deck out of 52 cards.
And then it's without replacement. So if I get a diamond on the first draw, what's the chance I also get a diamond on the second draw?
So now there's only 12 diamonds remaining out of the 51 cards. So we have a smaller chance of getting one of those last remaining diamonds.
Exactly. And then for the third one, we actually have taken 2 diamonds out already. So I have 11 out of 50 chance of getting a diamond. For the fourth one, I have 10 out of 49 chance of getting another diamond. And for the fifth one, I have a 9 out of 48 chance of getting another diamond. So you can see these special cases are complicated if we don't use the complement. And then the without replacement also makes it a little complicated too, because we have to think about the probability given that an event already happened and that event does influence our next probability. So are you ready for the answer, Wade?
Yeah, so I'm not doing the 1 minus yet. Just
Okay.
the fractions is quite small.
Okay.
We have 0.000495.
495. All right, so we have 1 minus that.
So 1 minus that becomes 0.9995.
0.9995. In other words, this would be a 99.95% chance of not getting all diamonds. And that makes sense. It would be weird if we did get all diamonds. All right, 2 more quick questions. The puzzle number 5 says, what's the probability of flipping a coin 10 times and not getting all heads? So here again, I have this not all probability, which is going to be complicated. If I am flipping a coin 10 times, not getting all heads, that would be, I could get 0 heads, I could get 1 head, 2 heads, 3 heads, 4 heads, all the way up to 9 heads. That would be so many different probabilities to calculate. Let's just use our rule. I'm going to focus on 1 minus the probability of getting all heads. So again, these are equivalent. My answer is going to be 1 minus. And then with a coin, we know that these are independent events. The chance of getting all heads is just going to be the chance of getting a head, which is 1/2 raised to the 10th power, right? Because the chance of getting a head on the first flip is going to be 1/2, and the chance of getting a head on the second flip is going to be 1/2, and so on. So Wade is pulling up Python here to see our probability. We have 1/2 raised to the 10th power.
So just the fractional part is 0.000976.
976. And then what about doing the 1 minus?
1 minus that is going to be 0.9990.
So 99.9%. That also kind of makes sense. If you're flipping a coin 10 times, you shouldn't get all heads, right? The chance of not getting all heads is 99.9%.
So that means that 0.1% chance of getting 10 heads in a row.
It's possible, but not likely. Last puzzle says, what's the probability of rolling a die 4 times and getting at least 1 6?
At least one.
At least one, that's our rule. So we know the probability of getting at least 1 6 is going to be equal to 1 minus the probability of getting none or no 6s. And again, at least 1 6, that means that we can get 1 6. We could get 2 6s. We're rolling 4 times. We could get 3 6s or 4 6s. And I don't want to calculate all of those different probabilities. They're very complicated. You have to figure out all the different options. The only thing that doesn't qualify as at least 1 6 is getting 0 6s. So that's an easy one to calculate. What's the probability of not getting a 6 when you roll a die?
So that's the other 5 possibilities. So 5 out of 6.
5 out of 6. And then I am going to raise that to the 4th power because I know die rolls are always going to be independent. The die doesn't change. Probability of not getting a 6 every single time is going to be 5 6. So what do I get for my answer, Wade?
So 5 6 raised to the 4th power is 0.482.
482. And then 1 minus that is?
1 minus that is 0.518.
0.518 or 51.8% is our chance of getting at least 1 6 when we roll a die 4 times. So as you can see, these rules, these special cases help us a lot in solving these probability questions, and I hope you enjoy nerding out with them as we continue this series.